So I'm Alan Cudmore. I work at Goddard Space Flight Center, and I've done a lot of work on the OS abstraction layer and the original core flight executive. But lately, I guess I've just been more of a CFS user than a developer. I have to admit, I haven't been really involved with the CFS community for the past couple of years. I've been really busy on a CubeSat project, and now I'm kind of getting drawn into another CubeSat architecture that Goddard's developing, and this high-performance spacecraft computing project that Jonathan mentioned. So a lot of this is really not updated. In fact, here's my disclaimer. When I started putting together this presentation, it reminded me of my ancient GPS. It always tells me your maps are over a year old. So likewise, this roadmap is over a year old too. And we really need to do some work to try to clean it up. So what I was going to talk about, and that's my, everybody's seen the old layer chart a million times, so I thought I'd make a different one. It was late last night. So I want to talk a little bit about what the platforms are, like what are we talking about for CFS platforms, what the current status is, like what we have out there, and then what's next, what we would like to try to do next. And I have a couple of thoughts on the device layer, which we really never made much progress on since last year. I mean, there's still some thoughts, and I can tell you what I did do with the CubeSat mission I worked on and what we're thinking about doing next. So what are we talking about? The CFS is a set of portable libraries and applications that run on top of the platform layer. And the platform layer mainly consists of the APIs, which is the operating system abstraction layer, the platform support package layer, which is the code that glues a particular operating system and board together to allow the CFS to run, and in some ways a set of device drivers. It depends on a set of an operating system, which tend to come in three classes for what we're talking about. We have real-time operating systems like the traditional RTEMs, VxWorks in its single memory form, single memory space form, and new operating systems like FreeRTOS that we've been using. Then we have the Linux and POSIX operating systems that really just started out as a convenient prototype platform, but it's kind of grown into more of a platform for really deploying the CFS on. And now we're also talking partitioned operating systems like ARINC 653, now ZenMI, and some of the lines are really starting to be blurred. Like I know VxWorks 7 has some hypervisor or partitioning add-ons that you can use. So it's really kind of, we have to be careful how we juggle, how we can work with all of these different operating systems and the different modes and memory models they have. And then as far as hardware is concerned, we seem to have a few general classes of hardware. I guess we have, the generic and simulated hardware platforms. And Linux is almost its own abstraction layer. If you can get the CFS running on Linux, it'll run on almost any board running Linux. It runs on the ARM boards, little Raspberry Pis, VMs, larger machines. And so we use virtual machines. And lately we've been using simulators like QEMU as a hardware platform as well. And I think that's going to kind of play into how we maintain these things. We have our Class B and Class A processor platforms like the RAD 750, and I guess now the Class A platforms that we've been working with. And lately at Goddard, we now have a whole range of these COTS CubeSat platforms that we're working with. In my presentation tomorrow, I'll talk about my experience of porting the CFS to one of these COTS CubeSat boards. And it really is probably the smallest board, the least amount of memory that we've run the CFS on. And so where are we with all this PSP and platform stuff? And the only thing I can come up with is we're all over the place. So the CFS project itself, when you download the open source releases, you really just get a few platforms. You know, we have VxWorks 6.x. I think we've tested up to 6.9 on PowerPC. And that's kind of a generic VxWorks support package. We have some RTEM support in there for 4.10 and 4.11, I believe. And I think Joe's running that on the PC version of RTEMs.
Tested 4.11.2 for the PC.
Okay. And then, of course, we have POSIX, which everybody's using now. And so there really aren't a lot of out-of-the-box platforms for the CFS. And there's a ton of unsupported platforms that, you know, as more people use the CFS, everybody kind of creates their own variant or their own version. And, like, I'm just going to list some of the ones that we've used at Goddard. You know, I implemented an RTEMS 4.10 Coldfire platform support package for the NMS mission. We have the NICER and JEDI space station experiments that Dave showed the NICER video earlier. And that's VxWorks. I believe that's a broad reach board, PowerPC.
3440.
And then we have the Space Cube at Goddard. We have the CubeSat that I worked on, which is using FreeRTOS, and also the STF1 CubeSat from IVNB that's also using FreeRTOS, that's using a, what is it, the AVR32 architecture on another CubeSat COTS board. And we have the Series CubeSat. I probably mislabeled the upper and lowercase mixture there, which is using the CubeSat space processor, the Shrek space processor, the ARM Zinc platform with Linux. And then there's a couple of balloon missions. I wasn't quite sure. John, you probably know what platform those are. Opus?
Opus was on a PC with Zenimo.
Yeah.
Okay, so it was on actual x86 Zenimi platform.
Like a dual core or something or other.
And then, so, you know, I can't even possibly keep track of everything outside of Goddard that we've used, that CFS has been used on. And so that kind of presents, you know, a dilemma of how we want to try to manage these things. And I really don't have a good answer yet. So some of the things that we would like to do in the near term, or, well, I guess first of all, this is kind of a grab bag of things that are floating around that we would like to integrate and take advantage of. You know, and a lot of this was mentioned earlier, which is kind of good to see the same themes repeated over and over again, because it means we're all at least on the same page with those. We'd like to make sure that we have 64-bit compatibility. You know, we want to transition to CMake for all of our missions. Under the CubeSat that I worked on, we just used the traditional makefile system. It's just because we were kind of in a hurry. That's what I was most familiar with. So that's what I used. You know, Joe has developed the next generation OSAL, which is really just kind of a relayering of the OSAL to kind of factor out all the common code in each OSAL implementation to make it easier to implement new OSAL instances or new OSAL ports. And then, of course, we talked about symmetric multiprocessing. We would like to get that into the OSAL and PSP. We have some operating systems we would like to update or integrate support for. RTEMS 4.11, I know that there's a couple of efforts going on to make sure that the CFS works with that release. Personally, I'm working on Goddard's new CubeSat architecture, which is a Leon 3, and I have RTEMS 4.11 running with the CFS on that, and I've implemented the dynamic loading. In fact, later this afternoon, I have a demo on my laptop I can show. So I have it running on the QEMU emulator for Leon 3, so I can show running RTEMS and CFS on that. And also, we'd like to integrate support for the upcoming RTEMS 5.0. I guess, Joel, that's it's now called 5.0, right? Not 4.12?
Yeah, unfortunately,
Okay.
confusing.
And then, of course, symmetric multiprocessing support. And I know I haven't personally used VxWorks 7 yet, and I think we also need to make sure that we have support for latest versions of VxWorks and SMP. FreeRTOS is something that we're working with in the CubeSat world right now. And, so we have a couple of FreeRTOS ports of the OSAL, and we really need to, if we're going to use that long term, we need to get that folded back into the open source releases. And then, of course, we have the A-Rink and the ZenMI ports as well. So there's a lot of stuff out there. And of course, hardware platforms vary greatly. CubeSat platforms, we have some Leon 4 work starting at Goddard. We have this high-performance spacecraft computing project, and there's a lot more. So there's, I guess as the CFS and CFE core kind of remains stable, the base below them just kind of keeps multiplying. So what we like to do in the short term, I think we'd like to take a look at getting the next generation OSAL integrated. We definitely need to get the SMP support integrated. That's a high priority. I think we should take a look at updating the RTOSs, VxWorks 7, RTEMS 4.11 and 5.0, including the dynamic loader support. We want to look at integrating FreeRTOS from our CubeSat projects we've been working on. And for the PSP, of course, getting the CMake, next-gen OSAL, and 64-bit support shored up. SMP support if there's any PSP work that needs to be done there. And then I was thinking in terms of platforms, Linux is pretty much a generic hardware platform just because it's so well abstracted. And VxWorks and RTEMS can almost we can almost make a generic platform for those operating systems as well, because they contain most of what we need to run the CFS without really getting too hardware specific. So for example, the RTEMS CFS port I have for the Leon, it runs on QEMU, it runs on the TSIM2 simulator, it runs on our CubeSat board, and it runs on another commercial Leon board. So it's getting pretty generic, and I think I've also run it on the Raspberry Pi as well with RTEMS. So I think we can probably try to create as generic as possible PSPs for these operating systems to make it easier to maintain and to move towards into future projects as users need them. And I'm kind of struggling with FreeRTOS because FreeRTOS is just a generic kernel. It just has the basic primitives, and they're covered by the OSAL, but you really need to kind of build up an infrastructure for the rest of FreeRTOS. For example, you need to have a file system, you need to have some sort of dynamic loader support, and FreeRTOS doesn't even really define what C library you're using. It really just comes along with the compiler that you're using. And in the case of the CubeSat board I worked on, ComSpace, they provided the firmware for the board along with FreeRTOS, and so their firmware pretty much addressed all of those problems, everything except for the dynamic loader. So it was a little bit easier, but it's not a generic solution. So I was slowly starting to think about a generic FreeRTOS solution. But that's the nice thing about VxWorks and RTEMS is they have the infrastructure that we need for that stuff. And then, of course, we have a device plug-in model that we need to consider, too. Our small sat group is considering adding the portable interfaces that you see on most CubeSats, like SPI, I2C, UART, GPIO, things like that. And, just talking to somebody earlier about SpaceWire, so we probably want to consider what we really need to have in the PSP in terms of device support. Some of the longer term work that we need to do, we really need to document the PSP APIs, and it would be nice to create the integration test suite, and most importantly, a porting guide. That's one of the most common questions we get is, what does it take to port the CFS to a new platform? And if we had a porting guide for the PSP and some better documentation and even a test suite so you could know if your port is successful, I think that would go a long way in allowing people to say, yeah, I have a very good PSP port for this board, and I know it'll run CFE 6.6 or 6.7, passes all the tests. And I think maybe one of the keys to this is we need to think about keeping the OSAL and the PSP APIs as simple as we can so that they're portable to all the operating systems and the boards that we work on. Because we really don't want to have feature creep go into the PSPs and end up with a ton of APIs that will only be applicable to one board and not another, or the rest of them actually. So I think the key to all this is, we have to come up with a way of kind of being able to satisfy the needs for the applications and the missions, but try not to let feature creep build up the APIs to the point where they're unmaintainable. And we need to try to figure out, like, who's going to maintain all these ports? Like, if the CFS community has a handful of really nice generic well-tested ports, one for each operating system, for example, it'd be nice if they all ran on simulators and they could be used for continuous integration or automated testing. But then it would be nice if everything was documented well enough and came with test suites so that if someone else wanted to create and maintain a platform like a PSP or even an OSAL, that we would have some confidence that we could just download it, plug it in, and make it work with the rest of our CFS. Just a couple of thoughts on the device model. For the CubeSat that I just worked on, what we ended up doing is this used FreeRTOS, and the operating system itself didn't really have a device model. There was a bunch of custom libraries written by the vendor, and they had some nice functions to access I2C, SPI, UARTs, and things like that. But it didn't really follow the traditional Unix open-close read-write model. And so what we ended up with, and I guess another thing we wanted to do is we wanted to be able to run this flight software on both the target board and on Linux so that we could test and we could interface to the 42 dynamic simulator. And we actually we can talk to the simulator on the target board as well over a UART. So we did this by abstracting everything, all the mission hardware through the mission hardware library. We call it the Dillinger Hardware Library. And it's a CFS library. And it just abstracts at kind of a higher level all of our mission hardware. Like we can make a call to get the gyro data or the GPS values and things like that. And that was very successful for us because we were able to, on the PC, we were able to just, the ACS application would make the calls to the hardware library, and when it needed to, it could either return a simulated value for some of the data, or it could go and talk directly to the 42 simulator and actually kind of simulate its orbit. And we were able to test a lot of the ACS that way. And then when we ran it on the actual target hardware, we have a version of the same library, same API, that let us run it on the actual target hardware and talk to the real hardware. And we could actually turn off pieces of that on the target hardware depending on what was connected at the time. So if we went into the lab and wanted to run on just a bare board with nothing connected, we wouldn't hang up. We could just actually run. And so I know the Goddard small sat group that's kind of starting up, we're talking about a device model where we're thinking about putting some of the APIs at the PSP level so that mission apps can have a generic set of device functions that they can call. And I would imagine that we could abstract it through the mission hardware library as well. but they could call through to these SPI I2C calls. And so the real test of this, we can try it out with a couple of the platforms we're working on. We have free RTOS for an upcoming mission or two, and so we can have those talk to that mission hardware. And we also have RTEMS on our new Leon-based CubeSat architecture. And with RTEMS, it has APIs for UART, SPI, I2C, and so we can see how well that works for us. I mean, a lot of these things, when you're trying to abstract and generalize something, you really almost need to do it a few times with different architectures before you see what really works. And then this doesn't even really get into how it's going to work with, say, Linux yet. So I don't know, are there any questions about this?
On the,
Need the microphone?
I can probably talk about it. On the bus ports, are you trying to make sure you have like a common API across SPI, I3C? All of a sudden I'm working on two boards and I might be talking to a Star Tracker over SPI on one, but then the next board, you know, it's an I2C or whatever. So I upstream, I would still have the same APIs and I just had to insert the new hardware interface. Is that where that's going?
Yeah, I'm not sure yet. I mean, this is mostly being led by Matt and John from the ID&D team, from their STF1 CubeSat. So this was, the idea they had was, they had a bunch of firmware-specific calls in their mission applications, and they thought it'd be a good idea to abstract them in the PSP and try to make it generic. So I guess the original question was,
It's like a project I was just on. We were talking to a peripheral device.
mhm.
So a project we just did. We were talking to peripheral devices, and so at one point we were using the SPI bus and it wasn't working out. So we went over and looked at a couple of different things, I2C or CAN, and it'd be really nice if everything upstream that was actually making the calls or accessing that device could just pull out a specific bus, put in a new bus, and never even know. In other words, never know about that transport layer.
Okay, so like in the case of the CubeSat, the Dillinger CubeSat, it was all kind of hidden through the hardware library. Like the mission hardware library, for example, if you were talking to a Star Tracker, in our case, let's say the gyro, the ACS app could make a call to the hardware library that said, give me the gyro engineering units, basically the X, Y, and Z floating point values. And in the case of the flight configuration, it would go translate those to the SPI or the I2C calls, go talk to the gyro, get the 16-bit values back, convert those to the floating point values, and return them to the app. And in the case of running our simulator on the PC, we would just go and get the floating point values directly from the simulator, the simulated gyro values, and just return them to the app. So to the app, the interface, it didn't matter what was underneath, and we could change out the implementation. So in this implementation, you know, you could implement the Star Tracker interface through here, and it could make the appropriate calls. I guess I don't know enough yet to say whether or not like the SPI and I2C calls would be interchangeable, but at least you could at kind of an intermediate layer, you could make that portable. And it would be a little less work to change out which bus you're talking to.
I can speak to that slide just a bit more. The reason we had this problem is we had two CubeSat missions, both using free RTOS with different drivers, and the driver APIs were different, but our mission app was the same. So in this case, if we wanted to upgrade, this happened with the Dellinger power system, upgrade to the power system that we were using, they couldn't just reuse our app because the driver calls were, you know, nested down a layer into the free RTOS drivers. So if we had a CFE PSP call that says CFE PSP I2C read, that will be the same no matter where it's at. Instead of saying free RTOS version whatever 48BR I2C read, it just gives us a method to reuse apps across all these missions that have different flight computers.
Is there anything else, Joel?
I don't know if I need a mic. I was just gonna point out that for the first three on the SPI, I2C, and UART, Linux and RTIM should be the same from a user perspective. The GPIO, I don't really know that there's a standard way of doing those. Oh, and that ties in the other question. What about RTIM's, there's a POSIX PSP that the Shrek project developed. So there's two RTIM's PSPs now, depending on whether you're using the classic API or POSIX.
So the Shrek developers have used the POSIX API for RTEMs, and so they were able to use that to, I think that's the way they got to the dynamic loader and just decided to stick with the POSIX APIs for everything. So yeah, I guess we'd have to reconcile that as well for RTEMs, whether or not we want to stick with POSIX or use the classic RTEMs APIs. My current implementation for the CubeSat board I'm working on just uses the classic RTEMs APIs, and then I added the dynamic loader APIs to that. Any other questions?
So have you ever considered just adding an abstracted driver model to the OSAL? Because if you did that, you could write all the drivers you need under that, including some of the PSP things like timers, and then you could just get rid of the whole PSP, because there's often a lot of redundancy between the OSAL and the PSP.
Yeah, although, are you sure there, I mean, I think we tried to eliminate redundancy between the OSAL and the PSP. The question is, in case it wasn't heard online, is have we considered just writing a generic device model for the PSP?
For the OSAL.
For the OSAL? Actually, yeah, I mean, it's probably one of the things we need to look at too. We had thought about it and haven't really done anything yet. But.
So we've done POSIX interfaces to all of our I/O at that
Mhm.
particular point. And that's pretty much extracted out most of the things. I mean, you have to have, build up or go for POSIX and POSIX interface, but it really gives us a lot more flexibility as far as that goes. So it's a lot more portable.
Yeah, I mean, it does seem like that's the most portable device interface out there.
It's
It's
well
just the
documented,
Linux
it's well
POSIX
understood.
model.
And, for something like FreeRTOS, it may be something a little bit, add a little bit more, but at least for all of the others that we've been working with.
Yeah, so the question is, do we want to continue to support FreeRTOS and kind of build up the infrastructure we need for it for things like this, or do we just want to stick with operating systems that provide us with a minimum set of capabilities like the
Well,
POSIX device model? And
But if you do the abstracted device model in the OSAL, you could model it after what POSIX already provides, and then just implement that for FreeRTOS.
Yeah,
yeah, that's true.
And
Yeah.
it's more work for FreeRTOS, but it's still doable, and gives that common interface.
And I have run into an application scenario where I would have liked a select mechanism. So I hear you on there too.
So one question I did have on the FreeRTOS is how big or how much of a memory footprint were you able to get it down for Dillinger?
Yeah, so for Dillinger, we have the board actually only has 2 megabytes of SRAM, and so we ended up having to run the code in Flash. So the code by default runs in Flash, and so so the firmware, the OS, the flight code or the CFE code, and the applications took roughly 1.5 megabytes of code in the Flash, and we used up nearly all of the 2 megabytes of memory. We have like a 128K RAM disk for the CFE, and some of the apps we actually loaded from the file system into RAM. So the mission apps, we were able to squeeze into RAM and dynamically load them so that we could replace them in flight if we need to. It was a compromise, and I certainly wouldn't want to do that again. I would much prefer to have at least 8 megabytes of RAM.
we can move on. So hopefully we squeeze one more presentation in before lunch. Gate armor. Thank you, Alan. Thank you. Sorry.